Welcome to the 2016 American Physical Society Kavli lecture session. I'm Sharon Glotzer from the University of Michigan. I will be your flight attendant for the rest of the afternoon. I want to start by acknowledging the phenomenal support of the Kavli family and the Kavli Foundation, which, as you know, supports the forefront of physics by funding so many things in our field. And in particular, they've provided generous contributions to allow us to bring to you the very best lecturers in the field of physics for this special symposium that we run every year. One of the perks about being the meeting chair, the program chair for the meeting, is that I get to choose the Kavli lectures, and next year's chair will choose next year's Kavli lecturers. And of course, there's a constraint when you on what lectures you're supposed to choose. With the first constraint being that these should be absolutely phenomenal, illustrious physicists working at the very forefront of the field, working on some of the hottest science in the field of physics. And the second constraint is that they should be absolutely outstanding lecturers. And I'm sure that you'll agree with me when you hear their lectures that all of our five outstanding speakers this afternoon fulfill, way beyond the two constraints that are placed upon us. So I'd like to begin with our first lecturer today. Our first lecturer is Maria Rey from Gila. Ana received her bachelor's degree from the University of the Andes in Bogota, Colombia, and her PhD in 2004 from the University of Maryland. She was a postdoctoral researcher with NIST and a fellow at the Institute for Theoretical Atomic, Molecular, and Optical Physics at the Harvard-Smithsonian Center for Astrophysics prior to joining the University of Colorado at Boulder, where she's currently a fellow at Gila. Anna is very well recognized for her research in ultracold atoms. She was a recipient of the Office of Science and Technology Policy's Early Career Award. She's a MacArthur Fellow. In 2014, she received the Maria Geppert-Mayer Award of the American Physical Society, and she's also a Fellow of the APS. So please join me in welcoming Maria Rey to the stage.
All right, can you hear me well? So let me start this presentation by thanking the organizers of this symposium for the invitation to be here. It's really a great honor for me to share today a little bit of the research that I'm doing at Gila. Let's see, yeah. Okay, so this talk is going to be, the title of the talk is New Perspectives on Quantum Simulation with Alkaline Atoms. So this talk is going to be about alkaline atoms, about cold atoms. So let me start with the question, what can we do with ultracold matter? And perhaps you are aware of the potential and the capabilities of ultracold atoms in the sense that nowadays the most precise sensors in the world operate with ultracold matter. So we have developed the most precise clocks available now and interferometers. And well, this is one great capability of the systems. However, what I'm going to tell you today is one step ahead. So all these capabilities and increased sensing and tunability of the parameters have exploited our capability to interrogate atoms at the single particle level. Nowadays, we are starting a new revolution, a new quantum revolution, where we are not only use single particle properties, but the behavior of many body systems actually to enhance our measuring capabilities and the capability to explore the quantum world that is fascinating. So in particular, we are going to not only use many body correlations to make much better clocks and interferometers, but now we are opening a new perspective to use ultracold atoms trapped in periodic potentials generated by light to simulate the behavior of electrons in solids and to perform quantum simulation. Because these atoms have unique atomic structure, we are able to create new synthetic materials that are not accessible in nature And now we are also using these systems to open the possibility to construct quantum computers with capabilities that are not offered for with classical computers nowadays. So this talk, I'm going to briefly mention some of my research that actually bridge these three: closed quantum simulations and synthetic materials. I'm going to tell you how clocks can be used to probe quantum simulations and to actually build new quantum materials. And all this possible thanks to one type of atoms that is called alkaline atoms. These atoms live in the second column of the periodic table and has two outer electrons or other with the same atomic structure, such as ytterbium. So today the focus is mainly going to be on strontium, but there has been also already experiments done in ytterbium. And I will focus on fermionic atoms because these also have a nuclear spin I that is greater than 0, a finite nuclear speed. So before starting, I want to acknowledge my team, my collaborators. So this work has been done in very close synergy with the GILA Strontium Optical Lattice Clock with John Jay, the PI, and fantastic group of postdocs and graduate students, and with my theory group, and in particular for the work that I'm going to talk today, I want to emphasize the work of Sergei Smirnov, Michael Weyl, Andrew Kohler, Leonid Ilsaev, Bihui Su, and of course collaborators not only at GILA but other different places of the world, and also the funding agencies. Okay, so let me start this talk also by showing this plot that shows the amazing progress that we have reached in stability and accuracy with clocks. So we know that cesium clock is the standard that determines the standard of the second, but you can see that in the last couple decades, this has to be stopped and being the leader, and now we have been reaching records of stability with the optical lattice clock, and in particular, you see the great progress that we have reached with strontium. In the last year, we reported a record level of stability worldwide as low as 2 × 10⁻18, and we have beaten even the precision of a single ion clock. Why we can do that, and what is the progress so fast? Because the strontium clock is actually interrogated not a single ion like those that do, but many atoms at the same time. So this gives an average time and a faster acquisition data. That is what gives us allowed to average for and reach this type of records. This is on one hand, but the other hand, because it interrogates many atoms, it also allows us to explore actually many body physics. So what I want to tell you today, or the main story that I want to tell you today, is the synergy between many body physics and clocks. Why? Because if I think about the strongly correlated materials, you might share with me that the key ingredients that make these systems behave so exotically and so complicated is the intrinsic interplay between charge, spin, and orbital degrees of freedom. It's the complicated interface between spin, motion, and quantum statistics what makes everything so complicated. With actually, in the same atom, I can encode all of these degrees of freedom at once. I can use the nuclear spins of the atoms to encode an spin degrees of freedom. I can encode the orbital degrees of freedom of the clock, as I'm going to show fast for an orbital degrees of freedom, and I also can make the atoms simulate like charged particles by using laser fields. So actually, the clock operates with 2 electronic levels that are interrogated. These are the orbital levels, and the clock is so precise because this transition is forbidden in the sense that lasts hundreds of seconds and gives rise to tremendous spectroscopic resolution. That's what we gain, and that's why it's the impressive sensitivity of the clock. But we can use these two actually to resolve a Brody energy spectrum into a set of very well-resolved levels. And this is what I'm going to tell you what have been starting doing. All right, the story began when the first clock at GILA was created. They used strontium fermionic isotopes because actually for the clock, collisions and many body interactions are problematic. They change actually the frequency, the ticking of the clock that should be universal, and what we want to measure is modified by interactions. However, if they operate a clock with nuclear spin polarized atoms, it happens that quantum statistics forbids S-wave collisions that are the ones that doesn't have any barrier, and the only collisions that are allowed as the P-wave collisions that are suppressed by a P-wave barrier, centrifugal barrier, that is the order of 30 microkelvin much more higher than the actual temperature of the clock. So the clock operates by trapping the atoms very tightly in a one-dimensional optical lattice, creating an array of pancakes. In each of the pancakes, we have many atoms that feel like an harmonic confinement from the laser. So the idea is that if they don't if they don't interact, within each pancake, I have many atoms doing exactly the same, and I gain a lot of signal to noise. That's great. However, interactions actually could degrade the error budget of the clock. And actually, this is what was seen at the beginning when the clock was constructed. Regardless of the fact that there was this P-wave barrier, they found that the clock was so sensitive that it could measure density shifts, and these were the most important systematic at that time. So that means that it opens for the exploration of many body physics at the same time, and that was great. So that's where theory came into play. So then we started to analyze this type of collisions in the clock, and well, they were P-wave, and in principle, we need to characterize the collisions with 3 channels. So if we have atoms in the ground and the excited state, they could be 3 different types of collisions that could happen between G atoms, between E atoms, and between G and E atoms. So these were the interaction parameters that we need to characterize. So we perform a mean field model, a simple theoretical model. I'm not going to enter in details to try to understand what is going on. So what we asked the experimentalists is to use the specific protocol in order to probe the interactions. The idea was the following. The atoms were actually all starting pointing in this, so down and up are the ground and the excited state of the clock. So they start, all the atoms in the ground state down, and they apply a laser pulse to actually rotate slightly the atoms to some angle theta. So, and then they let the system oscillate or evolve for some time, and then they make a measurement. The number of the excitation of the atoms was controlled by this angle theta, that is the pulse area. So for condensed matter people, this is kind of a quench experiment. When you prepare the eigenstate of a system in a very large magnetic field, you turn off the field and then let evolve during the different Hamiltonian. So the Hamiltonian that we wanted to characterize was the single particle Hamiltonian when the atoms are going to tick depending on the difference between the laser and the atomic frequency of the transition. This was this term, and this is what we wanted for the clock, but it's going to be modified by the interactions. So at the end, what the experimental measurement is what is called a Ramsey fringe, that is measuring of the population of the excited state. This Ramsey fringe has 2 parameters, a phase that is related to this parameter delta, the detuning, and a contrast value. So we did a very simplified model where actually this Ramsey fringe was not only the single particle one, but the contrast and the phase was modified by interactions. And our theoretical prediction was that this modified ticking of the clock was proportional to the density and proportional to 2 different interaction parameters, P wave and S wave, and proportional to some excitation cos theta that is determined by a proportional to the excitation fraction, how many atoms are in the excited state. Actually, the clock did this experiment, and this is actually what they saw. The data is theoretical, the data experimental points as the different ticking of the clock when they change the excitation fraction. Actually, the theory, they saw exactly the linear behavior predicted by the theory. And what it allows was to determine the P-wave interaction parameters from the fit, and actually very nicely operated at this sweet spot where there were no density shifts. This is how the clock was able to actually remove interactions from the systematics and reach the level of precision that they have so far. So this was nice. So we used many body physics to improve the clocks, but now we want to go to the other way. So let's try to use the clock for explore interesting many body physics. And that's a very interesting development that we have, is that when we think about alkaline atoms, these atoms are not only excellent timekeepers, but actually they have a unique atomic structure that manifests in very exotic type of collisions. Why? These atoms have 2 outer electrons, and they combine in an electronic singlet state. So we have a J equal to 0 electronic state, and we have a nuclear spin I. And in general, in most type of atoms, these 2 are coupled by the so-called hyperfine interactions. So this product is actually 0 in the clock. That means that the nuclear spins and the electronic spins are fully decoupled. That might sound very trivial, but actually it's very interesting because it gives rise to a very exotic symmetry that can have remarkable consequences in quantum mechanics. So the fact that the nuclear spin do not participate in the collisions means that the collisions are nuclear spin independent, and therefore that we have a new symmetry that is called SUN symmetry, with n determined by the number of flavors or spin degrees of freedom that we have in the clock. So symmetries always are associated with conservation laws. In the strontium, that means that there is no spin-changing collisions. That means I have atoms in two different nuclear spin states. When they collide, they are not going to go into two other two, but they are going to remain the same. So we have a system that actually naturally, without any tuning, exhibit in principle SUN symmetry in the collisions. And if you think about SUN, actually SUN symmetry can have, as I said, remarkable consequences in quantum mechanics. For example, quarks exhibit SU3 symmetry. Moreover, for us theories, the SUN symmetry allows us 1 over n as an expansion parameter. And if n is large, we can handle very strongly interacting materials and do predictions about them. And actually, that's what we did. So using the 1 over n expansion, we predicted that the ground state of alkaline atoms in a 2D optical lattice, in a 2D periodic potential, that is tightly confined, that tightly confines in the ground state for a very strange state of matter, longly saw in condensed matter systems, but actually never found so far. There is a chiral spin liquid that is disordered even at t equal to 0 and has properties similar to the quantum Hall effect with adionic excitations. And this would open the route for an error-free quantum computer. So this could be very exciting, and what we want to first is check that this SUN symmetry is present in the collision properties of the atoms. And for that, we have used the clock. So what we have done is the following. Well, first, let's think about, on the theoretical point of view, what are the parameters that we need to understand. So we have SUN collisions, that means that they are independent of the nuclear spin, but still we have a slew of parameters that we have to handle, because when we open the clock to nuclear spin degrees of freedom, what happens is that we can have nuclear spin antisymmetric and nuclear spin symmetric collisions. When there are nuclear spin symmetric, we have the p-wave parameters that we had before, but as soon as opens a singlet channel, we also have S-wave collisions in the GG, EG, EGE plus GE channel, plus other two collisions in the antisymmetric channel. So we have all these slew of parameters that we had to identify by measuring in the clock. So we have done that. So the idea is the following. We run the clock, interrogate the atoms, but now allow a mixture of nuclear spins. What we did is that we interrogate a nuclear spin component in the presence of a magnetic field that prevents collisions, exchange collisions. So what we did is that actually, instead of interrogating the only nuclear spin channel, we allow to populate all the different other channels in the clock. And our prediction is that these are going to be spectator atoms that are not going to that could affect the ticking of the interrogated atoms. So the idea is that if there were nuclear spin symmetric collisions, I don't care how I redistribute my atoms in these spectator channels. The only thing that I care is that I keep the same number of atoms, because the collisions are nuclear spin independent. So I don't care how I redistribute my atoms, provided that I keep the same number of spectator atoms, I should see the same. So the ticking of the clock is going to be the ticking from this that I got before for our single nuclear spin component, modified by the interactions with the spectator atoms. And actually, if there is SUN symmetry, this is only going to depend on the number of particles in the spectator channel. And exactly that's what we saw. We actually probed and see that independently of how we distributed the spins, all the interaction parameters were exactly the same, proving that we have SUN symmetry up to the 3% error, just because we didn't have to, we could measure longer, but for now we can confirm that there is SUN symmetry at this time, opening the possibility to actually use these alkaline atoms to probe very exotic properties that doesn't exist in nature, and that can be useful for very different applications. So we have characterized all the different parameters using the clock, and this opens the possibility to really have a quantum simulator for the models. So now let me tell you a little bit about some new physics that we have seen that exploit spin and orbital degrees of freedom together. So actually, if we can create the best clock in the world, what we need is to completely suppress collision. This is on the precisional point of view. So we want to have a very, very tight lattice, 3D lattice, where we have one atom per lattice side. So in principle, this would be the best clock. We don't need to worry about interactions, but that's not exactly the case. What happens is that because the atoms go from the G to the E, we interrogate the transition, there is a net dipole moment, and therefore dipole-dipole interactions between the atoms. That means that we have to care and we need to understand dipole-dipole interactions, because even though this dipole moment is small, that's why the clock transition is almost forbidden. Still, when we are going to reach the 10 to the minus 18 sensitivity, those interactions can be a very important systematic for the clock. So that's how we start to try to understand the role of dipole-dipole interactions. And in general, the dipole-dipole interactions can be written in this way. So I have dipole-dipole interactions, an interaction between two dipoles, so particle I and particle J. So the dipole-dipole interactions has this generic structure, and in general, they are proportional to the line width of the transition. So there are two regimes that we need to care when we talk about dipole-dipole interactions. So if we have the particles that are interacting, so in general, dipole-dipole interactions occur between atoms that have an internal structure that exhibit a net dipole moment D. So this D is the net dipole moment of the transition. And here R is the separation between the atoms. And K0 is associated with the photon wavelength of the transition between the atoms. So these dipole-dipole interactions are very generic. They rule the behavior of interactions between atoms when they're either when they are very close or when they are very far apart. However, when they are very close, they have the characteristic 1 over R cubed behavior, and this is what we are always used to have. So this 1 over R cubed behavior when the atoms are very close respect to the wavelength, and therefore they happen in general in microwave transitions. But however, these interactions can be even more rich, and they can have 1 over R dependence, and they can have both elastic and inelastic term coming from the near and the far field. So what I'm telling you that because we have found that these dipole-dipole interactions in the clock can give rise to very exotic topological phases. How is that? So for that, imagine that we have an atom, like the strontium atom, that has a pristine J equal to 0, J equal to 1 transition. So and I want to understand how the dipole-dipole interactions are happening between these two atoms that has this internal structure. So what I have to do is actually I have project these dipole-dipole operators into these internal levels. So D is a vector and therefore has 3 components, the X, the Y, and the Z, but I can also look at the plus, the minus, or the Z. So what happens is that if I project these dipole-dipole interactions into these two different J equal to 0, J equal to 1 channels, manifolds, what I have is very different terms. One term is the term that when I just exchange the atoms, so I have one atom in one of the excited state, I have another in the ground state, and because they are interacting and exchanging photons, they exchange these levels in this way without changing the total internal angular momentum or internal levels. So they just exchange the levels. They can be also in this different J equal to 1 transition, and they don't exchange the levels. But there are some other terms actually that you can write from these dipole-dipole interaction terms that they can actually change the internal level of the atoms. I mean, if you have an atom, if you have an atom in J equal to 1 and the other atom in J equal to 0, they can actually exchange photons. As a consequence, these other atoms can go to, so they go, if this is starting minus 1, the other can go to 1, thus changing their internal structure and exchanging and interacting. But in addition, they have to actually exchange between them some angular momentum. So this is what is going to give rise to a spin-orbit coupling naturally without doing anything the atoms in the clock. So these atoms are going to exchange virtual photons. As a consequence, they are going to couple the internal levels with the angular levels. So this theta, this phi, is the polar coordinates between the two atoms. So to be more explicitly, that's what is going to happen. Imagine that I can create a lattice when I have all the atoms in the ground state. All the atoms are in the ground state, and I'm able to excite one of the atoms to this J equal to 1 levels with a laser. So what I want to see is how this excitation propagates in my lattice geometry because of dipole-dipole interactions. So from the dipole-dipole interactions, I can actually look at the propagation of this excitation through this. So this excitation can be exchanged between different atoms by hopping from one atom to the next in a way that is long range. But not only that, but I can also exchange the internal level of the atoms. So I can change an excitation from atoms, do a spin flip from atom in this, from sigma equal to -1 in these atoms to sigma equal to 1 of this atom. So this type of excitations give an effective spin-orbit coupling without doing anything. So in these atoms, there is this internal level is intrinsic. So what we have done is try to understand this type of the spin-orbit interactions that naturally arises in these clocks and try to see what type of states we can get with them. So what we imagine is the simplest possible system. Imagine a 3D lattice with one atom per side, and I have one excitation, and I look at the band structure of this Hamiltonian. This Hamiltonian is this excitation propagating through these different atoms. Notice that the atoms can be frozen themselves, but the excitation is propagated while flipping the spins. So what we have done is that we have computed the dispersion relation of this excitation propagating in the lattice. So Q now is a good quantum number because it's the quasi-momentum of the system. And this is the energy versus Q for this excitation that has 3 different excited levels. So these 3 levels, of course, coming from the fact that I have 3 possible branches in the excitation. So what I see is that if I look at the dispersion relations as a function of the different symmetry points of the lattice, of the Brillouin zone, what I see is that if I have a 0 magnetic field, there is a crossing that arises between these 3 branches. And what happens then, imagine that I apply a small magnetic field that breaks time reversal symmetry. What happens is that this excitation breaks down and it just opens, so it's a split, the generality is a split, and I have just a crossing between the remaining 2 excitations. And when we look at what are the properties of this, the energy spectrum of this excitation, actually we found that they obeyed 3-dimensional spin-orbit coupling. So what happens is that it let me try to parameterize what is the energy versus momentum for this excitation where I am very close this quasi-momentum Q. So if I expand close to the crossing point, what happens is that the dispersion relation of these excitations, so now I have 2 excitations here, that is sigma up and sigma down, and when I look at the energy levels of these excitations, I see a 3D spin-orbit coupling parameter, Hamiltonian, and this 3D spin-orbit coupling Hamiltonian has this form that I can also look at that by doing a different cuts over my Brillouin zone. For example, if I look at a plot of the Brillouin zone around PC, the expansion parameter, equal to 0, around PC equal to 0, what we see is that the Hamiltonian has this sigma plus, sigma x, sigma p, sigma y, sigma py, and this means that my block vector in this spin 1/2 levels is rotating. And this is exactly what we see. We have that there is a chiral angle on my excitations around this point. And if I look at a cut along the x direction, I see that the population of these 2 levels is changing from plus to 0, or plus 1 to -1, as I cross from up to down. So in other words, what we are getting is that we are having wild passive particles by doing nothing. So wild passive particles appears naturally in these dipolar systems. So and wild passive particles have been very popular in this last year, where we have found that, wild fermions are fundamental massless particles that were predicted long time ago in 1929 and with high energy point of purpose, or however they were never found. how they have been recently found in solid-state materials, but now we see that this type of excitations can actually naturally appear in our systems without doing anything, just exciting a few atoms in the lattice from the ground to the excited state. So what are the possible issues with this type of implementation of Weyl quasiparticles? Maybe the fact that if you don't have a perfect unit field mode insulator with one atom per side can introduce some type of disorder, and also the fact that we have dissipation from the excited states due to a spontaneous emission of the photons. So we have tried to look at these two possible issues, and actually we have found that these Weyl points survive even under those conditions. So what we have found is that if we have the atoms trapped so we use some specific transition for strontium atoms, what we can see is that actually we can have all the conditions necessary for creating Weyl quasiparticles in these atomic systems. So we can reach all the conditions that are necessary for actual observation in the lab. And this is something that we are currently doing at the moment. So we have, for example, seen that the elastic part of the dipole-dipole interactions can be 3 orders of magnitudes larger than the inelastic part. So these particles are long-lived and stable. Whereas, in this point, we attribute this some type of subradiant or suppression of the spontaneous emission. So in that respect, we have really a system that has possibility to be observed in the laboratory. And we have also tried to look at what is the effect of the disorder, that we don't have a perfect field lattice, but we have defects, and still we see that the Weyl points survive and are robust. So we have some predictions that we can see these particles, these Weyl quasiparticles that have caused so much exciting in these atomic clocks. So with that, I just want to finish and mention that I think there is great vista ahead. So we have only explored the regime when the temperature is very hot and the complexity is very low, and still we can see P-wave magnetism, SUS magnetism, and retarded dipolar interactions and Weyl points. But I think these atomic systems are such that they're opening the possibility to see very exotic behavior, SUN physics, even SUN dynamical gauge field, SUN Condor lattice model, so all the different models that explore the interplay between spin, orbital, and charge degrees of freedom. With that, thank you very much for your attention.
See, I told you that was going to be a great lecture. We have time for some questions. We have microphones set up so that everyone can hear your brilliant question. We'll wait for people to approach the microphone. We did start a few minutes late for those of you who are coming in late. It's hard to see anything, isn't it? It's hard to see anything. I can't see a thing. Okay, well then I get to ask a question. So tell me, what is the big thing, the next big thing for your lab?
So what we are trying to do is that the clock that we are trying to do this 3-dimensional optical lattice clock. So now we are trying to put, I am a theorist, but in the experiment they are trying to put the atoms in a 3-dimensional optical lattice and entangle the atoms. Try to see this, on one hand, this type of exotic topological behavior, and on the other, trying to enhance the sensitivity of the clock from 10 to the 18 to 10 to the 20. So 2 orders of magnitude gain in the clock by going into the 3D optical lattice.
Wow. Very exciting. Okay. There are no other questions. Please join me in thanking Maria Rey again.